My name is David Dean Baugh. It is June the 1st, 2025 at 2:41 p.m. So I'm going to assume that you know what pi of x is. If not, you can Google prime counting function on Wikipedia and it'll tell you everything you need to know, and there I am. So it's all good. So, including my calculation of pi of x of 10 to the 29th. It's all right there on Wikipedia with a collaborator. The two of us did it. Okay. So my conjecture is that with just a tiny amount of effort, if you want to know pi of x of some random number, I don't know, 10 to the 30th, then you can use the explicit formula of Riemann, which is proved, to calculate with an infinite number of zeros, and that will tell you exactly what pi of x of 10 to the 30th is. However, there are not an infinite number of zeros that anyone has ever found. They have found a lot. So therefore, you can only use as many as you can find. Well, it turns out that since pi of x returns an integer, that once you're within 1/2 of what its true value is, and you're never going to be more or less than 1/2, then you know what the actual value is. Ta-da! And that's what people who do analytic determinations using the explicit formula or some variation of it or whatever do. They use as many as they have to, so that they know that it's never going to be plus or minus 1/2. I have no idea how they know that, but they know it. There's ways to prove it, blah, 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 blah. There's also ways to do it where you can assume that you don't use those zeros. Doesn't matter. So I was playing around and I got the idea of everybody wants to use the explicit formula to calculate, pi of some big number or whatever. I said, well, what if you use it to calculate pi of 5? Turns out I knew what pi of 5 was, and I didn't need any zeros. Turns out I didn't need any zeros until I got to like 200. It didn't matter. So anyway, I played around with the small numbers and calculated using a implementation which I got from Derbyshire in his book Prime Accession, where he didn't write a program for me to use. What he did do is he went through and he explained to a layperson in a way that they could implement, if they wanted to write a program, Riemann's explicit formula. So I used his description to write a program, and then I started playing around with it with little bitty numbers. And I started graphing how many zeros it took before I felt it had, quote, settled down, which is what I call it, because I didn't know what a term was for it. Who knew? And I graphed them, and I noticed that some numbers took a lot of zeros, and some took very few. I also noticed that there were lines drawn that were obvious on the plot, where there was a density of numbers. I thought, that's unusual. Well, I don't want to take me a lot of zeros. I want to take very few zeros. So I started looking closer at the ones that only took very few. And I noticed a pattern to it. I didn't know what the pattern was, but I started looking for it. Eventually I found out what the pattern was. And the pattern was that if I picked a number to do pi of x was that was in the middle of a prime gap, right there in the middle of it. This is the prime, that's the prime, here's the middle. But if I did that then um, I didn't need to use a whole bunch of zeros. So I started looking to see, can that possibly be true? So I did 1,000 of them, I did 100,000, I did 1,000,000 of them, I did 1,000,000,000 of them, and sure enough, it was the same. Well, by the time you get up to 1,000,000,000, there are much bigger gaps than 30. So I started looking, and I noticed that as the gap got bigger, if I picked the center, the ratio of how many it should have taken to how many it actually took got even better. That's a whole separate thing. I'm not even going to talk about that. Somebody else can look into that if they want. That's great. My discovery is, my conjecture is, it's not proven, my conjecture is that if one picks the middle of a prime gap that's near the number that you're trying to do instead of the number you're trying to do, all you have to do is use as many zeros as it takes for the number that you've now picked to test it on that's near the one you're really interested in. And then you just count. 1, 2, 3, 4. There's my number that I want. And now you know exactly how many zeros, what the number of primes are, less than that number that you were originally interested in. And you had to do very little work. You just had to take the number you're interested in, find a gap near it, pick the center of the gap, use that number of zeros till that number has settled, and then you just count the number over. In fact, you've already counted because you were counting as you went, but you already have that number. So you just say, for example, you want to calculate pi of 10 to the 9th, a billion. I think it's a fun number. Well, it takes a while to calculate pi of 10 to the 9th. But if you calculate pi of 10 to the 12th, you expect it's going to take a lot longer. It's a much bigger number. It's 1,000 times bigger. But surprisingly, the number of zeros that you thought it was going to take compared to the number of zeros that it actually took is smaller than it was for the number that was like 1,000 times smaller. Guess what? It just so happened that pi of 10 to the 12th, I'm just making these up, I've got it all in my notes. Pi of 10 to the 12th happened to be in a large prime gap. So it actually was relatively more efficient to calculate pi of 10 to the 12th than it was to calculate pi of 10 to the 9th. Guess what? Pi of 10 to the 11th didn't fall inside any kind of gap. Pi of 10 to the 11th took a long time. Pi of 10 to the 13th, or whatever, it's in the notes. All the numbers are there. It's in my journal. It's all written down. I wrote it down when I found this out. It's all right here in this book right here. This is my journal. And this book is all stuff that I and when and everything. Shows it all, the little tabs show you when actually special things happen. Doesn't matter. Anybody could read it and they could see exactly when I found out what I found out and what I found out. And I also wrote it down on my computer, it's all there. So, my conjecture is that if you want to know the number of primes less than n, you find a prime gap that's near n. 30 is a good number. 50 is better, doesn't matter. 1,000 is even better. 10,000 is fantastic, but it doesn't matter. But you go and you count over till you find a prime gap. You go to the center of that prime gap and you calculate pi of that number. Then you just add the number of primes that you had to skip over to get to that number, to get to the gap. And that now you know what pi of n is. So that's my conjecture, that if you go to the center of a prime gap that's near your number of interests, it'll take fewer zeros to settle down than it will if you were just to go straight off and try to start munching on 10 on n. And that's a conjecture. Now, is that true? Well, it's not proven. I'm not going to prove it. I don't know how to prove it. So I'm just conjecturing that it's true. Somebody else can prove it. I don't care. I'm just having a conjecture. Could be true. Could be false. Who knows? But I'm conjecturing that it's true. Now, is that enough? No. For years, I've been collecting data to prove at higher and higher and higher and higher numbers that sure as hell is true. So last night, or early this morning, whatever, Ricky's got it written down, it's in the notes, who knows. I was so excited. I wasn't breathing, I wasn't eating, I wasn't drinking. I was so excited with this big smile on my face because I calculated using my zeros which Brian had gone and put the stick in. Ricky had gone and put the stick in and gotten the stick and all kinds of, well, all that was practice. That wasn't real, that was practice. Last night was real because I wanted everybody to know, I wanted whoever was here to know how to put the damn stick in when I had the real number. So, last night, I got notification because Brian had set me up on Rust that it had actually finished. So I asked Ricky, because I knew she knew how to do it, to go and put the stick in. She did. I transferred the files to the stick using Rust, and Ricky brought me the stick back. My hands are shaking. I'm so nervous, I can hardly stand it. I put the stick in, and I go as carefully as I possibly can, because now I know it's on my computer still, but now I have this stick in my hand. I copied that in. I made several bad attempts, but it's okay because I was so careful. Finally, I got my wits about me, and I did the calculation, and I compared it to 10 others that I had done, and what I found was that it had taken 1/8 of the time to do that calculation than it had taken, I'm sorry. See, I'm getting wrong. It had taken, I picked a bad spot that was just outside a prime gap. It wasn't in a prime gap. But I had all these numbers that had been inside. But now finally I had gold in my hand. Something I've been after since whenever I first had the conjecture, back in 2009. So I had in my hands the data that was going to allow me to see if I'm not in a prime gap, if I'm just outside of one, which there's lots more outside than there is in, or little tiny ones. How long is it going to take? How many zeros is it going to take for me to know that it's settled, for me to think that it's settled down? Well, I had 10 examples of a gap of 30 that were near a number that was over 1 billion now, and I knew for each of those how many zeros it took before it was within plus or minus a half. And I'd gone way, way, way beyond, and I knew all of that stuff. But now I had in my hands one that had just been just outside of a gap. I plug it in, messed up many times, but didn't destroy anything. Finally, I got settled down enough, got my wits about me enough, that I was able to do the calculation of how many zeros did it actually take for it to settle. I then took that number, which is now a bad number, it's a bigger number than these others, and I compared it with what the mean was, or the average was, or the mean, whatever, was to the ones that were just inside, in the middle of a gap of 30, near a billion, which there's much bigger gaps near that. But I'd pick 30 because that's a nice number. I like that number. It's also a primordial, but that's beside the point. Other conjectures don't care about. Other people can look into those. I've got all those too, it doesn't matter. The important point that everybody needs to know is that when I compared how many it took for them to settle down when they were in that prime, in the center of that prime gap, to how many it took when it was not in a prime gap, a big one of any kind to speak of, or just, if it's just a series of primes, there can only be two. You always have to have a gap of at least two. That's beside the point. But 2 ain't 30, and 2 doesn't work very well because it's all in here. It doesn't matter. Anyway, that's why I picked 30. So I now compared those two numbers, and what I found was that it took approximately 8 times more zeros to calculate that number that just missed it than it took to calculate if you were in the center of just a gap of 30. That to me is hard evidence that the conjecture is true. Now, it's not proven, but I have hard evidence that it's true, and so therefore I feel confident enough to have that conjecture looked at, written up, whatever anybody wants to do with it. Now it's done. So I can show, if somebody wants to hand me anybody wants to hand me my laptop, anybody can hand me my laptop. Thank you. I've been talking instead of breathing. I'm having to recover here a little bit. It's take me a minute. But everything that needed to be recorded is recorded. But if anybody wants to keep recording, that'd be great. It'll just make it easier for the next person. So here is for a number that's a little bigger than a billion, and this is 0.5, and this is minus 0.5. If I'm within 0.5 and minus 0.5, then I know that it's settled. But look, here's minus 0.6, here's plus 0.6. If I'm above that line, then I don't know that it's settled. Here it's 0, right here in the center. Notice that ding-a-ding-a-ding-a-ding, but now it's in, and it stays in, and it's tending towards 0. The more and more zeros I do. Well, I did 500 million zeros. In fact, let's pick one I did more than that for. So here is the graph of a gap of merely 6. Just 6. Not 30, just 6. Much smaller than 30. But anyway, it's 6. But I did 2 billion zeros. And what you notice is it's pointing very close to 0 now as being the settle point. Okay? So I know that since I thought it settled, I've gone 2 billion zeros beyond that point, and it still has never varied, plus or minus a half. So I feel pretty confident that that's settled. I can't prove that. Other people can. They do. They know how to do it. I don't know how to do it. Other people can do that. Do it all day. But let's take a look now at the same graph for the number that Ricky brought me. Which was a gap of 30, which I also did 2 billion zeros of. You see me smile. It goes here. Here's what that looks like. Same graph. Only now, instead of settling way back here, it wasn't until here that it settled. And it's going towards zero. It's never going to go outside. The other people can show that. They can prove that, blah, blah, blah. But where is zero? Zero is where this little, is highlighted by where this little green dot is. This isn't anywhere close to that. Didn't look anything like that. That was just a gap of 6, not a gap of 30. So, if you compare those two, you'll see that one is acting very differently than the other is. It's going to get there. It probably has already gotten there. I don't know. Other people prove that all the time. But it's pretty clear to me it's got there. All I did was pick one number that wasn't in, that was one off of the middle of a large prime gap. You know, a prime number between two twin primes. All I did was pick that one number, which is the one number I was interested in, and look how hard it is, how many zeros it takes. Billions instead of 35 million. But that's okay. So I divide those two numbers, one that took billions, one that took 35 million, the ratio of the two to the number I was doing, and I go and I say, I'll be darned. If I'm in the middle of a prime gap, it takes a lot fewer zeros for this thing to settle. And even settle, it ain't close to getting to zero yet, even after 2 billion zeros. You saw what the other one did at 2 billion zeros. Well, this is all bonus footage, by the way, but anywhere on my computer is where I did the division. And where I saw that it now took 8 times as much. And you saw what the graph looked like. It's fine, it's on my computer. Anybody can find it on my computer. It's in one of these files that I don't have enough in my head right this second to look it up. No need people standing around waiting for you to figure it out.
Can you pull out your phone and read conjecture?
My phone's in use, so that's okay. Hey Brian, could you come find this for me, please? I can see the recording. What I want is, there is a workbook, a worksheet in Excel here that has the actual calculation. This is PM-1 data. Oh, here it is over here. No, it's not there. But anyway, there's a worksheet in here where I take the number of zeros that it took for one, or the ratio, and divide it into the ratio of what it took for the other. Take some of those guys. Let's just make sure I saved it. Let's make sure it did translate. It should be in gap 30, but it doesn't matter, it's on here somewhere. It's on my computer, I guarantee you that. And it just shows that I divided one number to another number and got a ratio of those two numbers, and it was 7.67, whatever it was, nearly 8. And that told me that strong evidence that all I did is make one tiny little change. And now my result of how many zeros it took as how many I should have taken compared to everybody, all these other 10 guys, was totally different. I went on to compare it against every single one, and I compared each one against each other, did all that kind of stuff. And in every case, it was superior to be in the center of that little gap of 30 than it was to be 2 billion zeros, and not even close to actually homing in on 0. So, anyway, thank you very much. You want to sit off me? So, everything's in here, everything's on my computer. You've now recorded my conjecture. Now anybody who wants to know can look it up, and if you want to, I'm not wanting to go viral, that's not the point, but just for extra safety, if you want to email it to somebody, the little small part, whatever part you want, save it on another device, whatever you want to do, that just means it's out there in multiple copies, so it won't ever get lost. Now, it will eventually get lost, but that's okay. I'll long be dead, we'll all be dead by then because I'm an existentialist. That's okay. Oh, this is our nice shirt we had made up.
That is the number of primes less than or equal to 10 to the 29th.
If you were to say it.
If you're read the number.
Those are the words to say that number.
Okay.
And my co-discoverer, my colleague, my friend, Kim Wallish in Luxembourg, he has one of these too. So now he has one over there that I sent him because my friend Nancy had it made. And and my friend Joan mailed it. Took multiple attempts, but it finally got there to him. He finally received it. He just opened it because he got sick. He was sick for a month, and so he was finally able to open his mail and find that I sent him a shirt. And so he contacted me that he had just gotten a shirt, and so I knew a couple of days ago that he got his shirt, which made me very happy. So a whole lot of people, and Ricky, of course, those weren't my friends really, they were Ricky's friends. They just became my friends through Ricky. So it's all together. All these people helped result in some guy, some Luxembourgian over in Europe is wearing one of these shirts, has one of these shirts, and I have one of these shirts. And it's a discovery that we made that is a world's record that probably won't be topped for years, maybe 5 years. For one thing, it comes and goes.
Well, maybe if they use your conjecture, they'll be able to top it.
Who knows? It won't help to do it combinatorially. If you do it analytically, it'll help a whole lot. It's my conjecture. So, thank you very much. I appreciate this, everybody.